A lesson on the history of the periodic table. Chemist noticed that there were patterns in some of the groups of the elements. It was vague at first. Groups of three were found. The first best job of organizing patterns was done by Mendeleev, Russian. He organized all the elements, and the key thing that supported his thing was he made predictions which came true. Made predictions on types of elements, properties of elements, like ecosilicon. And anytime you do a theory where you make a prediction and it comes true, that's a strong case in your element. He organized things by mass and grouped by characteristics, left gaps where needed. Nowadays, it's arranged by atomic number, or the number of protons. As far as electrons go, which is the main concern that we're doing, the Aufbau principle. The Aufbau principle talks about the electrons are added one at a time to a hydrogen-like orbitals with the lowest energy going first. So electrons occupy lowest energy states first. Available. In other words, it wants to try to get as close to the nucleus as possible. This is also known as electron configurations. So it will fill up a 5s before filling up a 6s because it tries to occupy lowest rule. Hund's rule says electrons spread out one per orbital until forced to pair up with the opposites, and then when they are forced to pair up, they do opposite spins. This is related to electrons repelling each other. So if you have, say, two p orbitals, there are 3 orbitals in there. One electron will go into each of the 3 orbitals first before coming back and filling up. If you remember from last year, electron boxes, they fill in each of the 3 orbitals separately, and then they come back and fill in because they don't want to be as close to each other. They like the energy level because it's close to the nucleus, but they don't like having other negative electrons around them, so they spread out as much as they can. Valence electrons are the electrons on the outside of the atom, the outer shell. These are the electrons responsible for bonding and therefore all of the chemical properties that's going on. These are the interesting ones for chemists. So these are responsible for bonding. There is a movement afoot saying the inner shell electrons absolutely does not have anything to do with bonding. You might hit the high school books in about 15 years. But these are right now, the valence shell electrons are responsible for bonding, whether it's given or taken or shared. and these are the ones that are responsible for chemical properties. What does it react with? Things like that. Groups are the columns of the periodic table. They contain elements with identical They contain elements with identical valence electron configurations. So have identical valence shell electron configurations. The valence shell. For example, the alkaline metals all have something S1. 1s1, 2s1, 3s1, etc. Noble gases, P6, P6, P6. There are blocks in the periodic table. The blocks are what elements are being filled in. The S block is where the S orbital, P block, D block, the F block. The D block is known as the transition metals. The F block is the intertransition metals. There are general exceptions to the rule, to the electron configuration, what I call the washing machine effect. For chromium, you would expect a 4s2 3d4 electron configuration for their valence shell. 4s2 3d4. Now the S and the D are really, really close to each other, and in fact it makes much more energy sense, instead of having a full and an almost full electron orbitals, to call it 4s1 3d5. Half full and half full are much more stable. You can think of it as electrons getting as far apart as they can. There's only a half full, so it's all in an orbit by itself. Here, it's half full. Now, there's a little bit of energy needed to transfer the electron up, but that is more than compensated by having the electrons being as far apart from each other. You can also do copper and some of the other transition metals. It's like spinning smoothly around. That's why I call it the washing machine effect. If everything's on one side, if it's not evenly distributed, the washing machine goes to womp stage. Then you gotta distribute it out so that all the clothes are spread out evenly. So that's the washing machine effect. Periodic trends. Ionization energy. Is the energy needed to remove the least healthy strong electron, usually a valence shell electron, well, always a valence shell electron, going out there. So its abbreviation is I. So it's the amount of energy needed removed from the atom, least healthy strong electron. I sub 1 would be the energy needed to remove the first, which is going to be less than I sub 2, which is the energy needed to remove the second electrons, and I sub 3, etc., etc. This is removing it from a negative electron from a neutral atom, which it doesn't really want to do that, but it's takes much more energy to remove a negative electron from a +1 ion, and it takes even more energy to remove it from a +2 ion. So the more and more electrons you've already removed, it's not wanting to remove electrons from it, it wants to gaining electrons back, so you're doing the opposite of what it really wants to do. There's always a big jump in ionization energy after the noble gases. And that's because noble gases are the ultimate in the stable washing machine effect situation. It's the way it wants to be, and so taking more away from that very stable thing takes it worse. So the top right-hand corner of the periodic table has the highest first electron. The atoms are smaller. So in the periodic table, this corner has the highest I sub 1. It's because it's a smaller atom. That electron is closer to the nucleus, therefore is held closer. And so if you go from top to bottom, you get smaller atoms, so it increases. If you go from here to here, the atomic size gets smaller. The atomic size gets smaller, and the atomic size gets smaller there and there. It gets smaller here because you have more protons in the same volume of the atom. You get some small jumps on the ionization energy after half-filled orbitals. So the energy on the p level, the energy, say for boron, carbon, nitrogen, and then it drops a little bit, oxygen, fluorine, neon, and then it drops down for the next element. So there's increase in the energy, hits half full, drops down a little bit, increases more until it's full, drops down, repeats the pattern over and over again. Electron affinity is the energy change associated with the addition of an electron. Now this might be positive, it might be negative. So it's the energy change when adding electron. It's the opposite of the ionization energy. The halogens are the most energetic. They love to grab an electron, hence the -1 charge on most of the halogens. Noble gases don't react at all, so they have 0 energy. Some of the metals, you have to remove a lot of energy just to get it to accept an electron if they don't want to. In atomic radius, we've already covered. Top right-hand corner is the smallest radius of the atoms by layers. It has fewer layers and more protons per volume. So as you go up, which I explained up here above, the higher you go, you have less layers and you have more protons per volume as you go to the right. That's it.